with the dynamic programming classical examples, and we arrived to the problem knapsack, which is called also 01 knapsack or subset sum problem. What is this problem? Let's consider a knapsack that can hold a maximal weight of a certain value S, and we want to put items in this knapsack that are available to us, but each one has a different value and a different weight. And while respecting the weight limit, we want to put the maximum value inside the knapsack. So obviously, every item we can either take it or not, and this is a subset sum problem. So let's read here. Given an items and maximum knapsack size S, and we have n values and n weights, corresponding weights. The question is to what is the maximum value we can carry. We can either ignore 0 or take, and this is the name 01 knapsack. So let's consider the example in the schema. I have 4 different items, each with a value and a weight, and for example, this item is of the value 10 and weight 12, and the question is what is the maximum value I can put when the capacity is S equal to 12. If I take the item number 0, the first one, I have the weight 10, so I can add only additional item if its weight is less or equal than 2, the remaining, and there is no such item, so it will be chosen only by itself. So the total weight will be 10 and the total value will be 100. Another option, I can take the item 1, which can still leave a place for the item 2, so I take them both, which makes a weight of 10 and a value of 120, which is 70 plus 50. Another and last third option is to take the fourth item alone, which has a weight of 12, but the total value is only 10. And my goal is to maximize the total value, so the optimal solution here is to take the case number 2. So other problem variants of this problem statement is are one of the following. For example, given a set of integers and an integer value s, we can be asked, is there a non-empty subset that has a sum equal to s? Or we have also another variant that states that allows fractional knapsack problem and which accept a greedy solution. Solves this problem. As you have noticed, we used some certain of state. We considered items one after the other, and we considered if we still can take these items. So a complete search, recurrence, or backtracking method will be to consider the item, the current item, and the remaining available weight. What can I hold with the what items I can hold now? And there are two base cases. Either the remaining weight is 0. In this case, the value I cannot hold anything, so the value is 0. Either I have solved all and I have chosen my or I have reached the final stage, which is ig equal n, and in this case also I return 0. The recurrent cases can be divided into two sorts. Either the remaining weight, with the remaining weight I can pick this current item. What does it mean? It means that the weight of this current item is less or equal than the remaining weight, so I have an option to take it or not, or I do not have an option. If I don't have any option to take it, I just skip it and return only. I pass the turn to the next item, so I will return the value of id plus 1, and rem w will stay as is because I didn't use any weight. The value will stay as is and the weight will stay as is. If I have the choice, so what choice I shall take? Either I take it In this case, the value will be augmented by the value of the current item, and the remaining weight will be decremented with the weight of the current item. Or I see, what if I didn't choose it? So I take the maximum value that either of the choice can return to me. And how do I start calling this recursion? I start calling by the current item 0, and I have the remaining weight s, so I didn't choose yet any item. Are there overlapping sub-problems? Of course there are. This is obvious. With a certain item, I can easily arrive at the same state from two different branches of the directed acyclic graph of states, just like we saw in the last lesson. So there are overlapping sub-problems, and now we can apply dynamic programming solution. What is the complexity of the solution? We have studied that the complexity is the multiplication of m times k, where m is the number of states and k is the complexity to solve each state. As you can see, to solve each state, here the worst case is to take the maximum between two calls. There is no for loop, so the complexity is 1 to solve each state, and the number of states. What is now the number of states? We have n different items, and reaching each of these items, I can still have s different possible values going from 1 to s. So the number of states is equal to n times s. So the overall complexity is equal to also n times s, and if this is less or near 1 million operation, this can be doable using dynamic programming. We'll see the both approaches, top-down and bottom-up, and in this particular kind of problem, the top-down is faster. We will see how. Let's consider an example, the UVA 10130, in which we have exactly this kind of knapsack 01 problem, and instead of having only one total weight capacity, we have n people that can have each a total weight capacity, and we want the sum of the weights they can hold, knowing that they cannot share a common item. So we will call the solution over each of them and then return the sum. How do we proceed? The top-down approach will be as following. We have the memoization table. The first argument is the item in current item, and the second argument is the remaining weight, and we call using the item 0 and remaining weight, which is the full maximum weight capacity. And in order to solve each value, this is why it is called a top-down, we have to take, if this remaining weight is can hold the current weight of the item, we have to choose between two options. Either we take it or not, so we have to choose between not taking it, so we will have the dp of I plus 1 next line with the same remaining weight, same column, or with the next line but the column with remaining weight minus whether I take this current item, so I have to subtract the weight of this item, but I have to add the value because I take it. So we will return this value in this box here will be equal to the maximum of this one or this one, but added to the value of the current item. And we can see that we only have to calculate the required state. If a state is not required, we don't have to calculate it. And comparing to the bottom-up approach, which we will see just now, this is for an example of 50 random test cases. This goes 20 times faster. Top-down approach, as usually, we will fill the memoization table with dummy values, and we will begin by the state in green, and we proceed. As for the bottom-up approach, how do we proceed? In the bottom-up approach, we will initialize only the base cases. So we will initialize for the dummy item 0 because we will store the items from 1 to n this time and not from 0 to n minus 1. And the base case is the dummy item 0, and with the remaining weight 0 also. This is the base cases. And then we will proceed as following. We will fill all the states because this is a bottom-up approach, so anytime I have to I have to fill the value from up to down. I don't go back when I finish, I just return the value marked here in green. So for a general case, how do I proceed? Arriving at, suppose we have filled all the values in the line I minus 1, and now I will have to fill this particular value in yellow, which is for a current used weight W and a current item I. In order to know whether I choose I or not, or in order to know what is the value of this current state, knowing that I am cumulating the weight, so I used until now the weight W. So how do I proceed? I proceed in another logic. I say the value here is equal. If I didn't choose this item I, it will be equal to the value in the previous state. In the previous state where I have the item I minus 1, regardless if I chose it or not, because it will be depending on the also previous state. So having the value here is either I choose the item I, so the weight W when I have chosen the item I has included the weight of the item I, so the previous state was not the state I minus 1 W, was the state I minus 1 W minus WI, because with the current weight with the current weight of WI, I reach the total weight of W. So it is equal to maximum value of the current item added to the value that was here, at the column W minus WI, or I don't choose it at all, so it will be equal to the previous item's value at the same used weight, regardless this value how it was calculated. So as you can see, every time if I can still fit this item, I am increasing the weights. So the weights are filled from top to down, from left to right, and the final solution is given in the last item when I choose the last item and for the maximum available weight. Why? Because it is surely greater or equal to the previous used weight. Because if I don't use it, it will be depending on the previous. So let us summarize. At each time, at each state, at each column W, I see whether the current weight could have been fit in the total W used. If so, I see what if I have took it. So if I have took it, it means that I used its value and I added it to the state where the W was not containing the WI. So where the the current W is equal to this W minus the WI of this item, okay, of the previous. So we go up one line, but we go up also the number of columns necessary to decrease the weight. So in this case, of course, the next column will be if this W is greater or equal to WI, of course the next W will be greater or equal to WI. So, and I will have to repeat the same thing, and then for sure my values are increasing in diagonal. So the final answer, again I say, is in the uh, matrix CNMW. This is the code for the top-down approach, and as you remembered, we saw 2 slides before that we initialize the memoization table with dummy values -1, and then we initialize the call to dp0mw. Here we are returning answer plus equal because you know we have more than one person and we are cumulating the possible values. ADP function takes the state ID remw, and we have two base cases, ID equal n or remaining equal 0, in which case we return 0, and we link the answer local reference to the memo element, and if it is not calculated yet, we calculate it, but we differentiate between the current weight is greater than the remaining weight, in which case we have no choice to make. We just call the next iteration with ID +1 and same value, and else we call twice, once with the next ID remaining value and once with the value of this current item, and the remaining value decreased by the weight of this current item. This is a bottom-up approach solution, which gives the same exact solution, but it is slower because I have already explained that it will have to calculate and fill all the table. And in this case, for this is a bottom-up approach, so there is no recursion, there is a while loop. And for I equals 0 less than n, w equals 0 less than mw, those are the base cases initialized to 0. And then we have a double loop for I equal 1 to n and for w equal 1 to mw. And in this case, every time if wi is greater strictly, I have only one choice, and then else I have two choices, and the answer is inside CNMW. And let's see a demo. I have the top-down approach, this exact same code we just saw in the slides. In the second window, I have the input file, and in the third window, I will have the output file. I made a slight modification in order to compare how many operations we are calculating for the same input data with either the top-down or bottom-up approach. So starting with the top-down, every time I am calling GP, I will augment the approaches. I will augment the number of operations. So let us run, and we will get the 1 million operation. So those are the answers of the different cases. We have 50 cases, and the number of operations in all is around 1 million. Open the bottom-up approach, in which we also inserted the counter of operation, and now we will run it to see on the same example what is the with the top down we had the 1 million operation, and with the bottom up we have the 20 around 20 million operations. So this is it. This was for the knapsack problem.